All right. All right. In order for this demonstration to be useful, you got to be able to see this slinky. Okay. Josh is just going to be an in post. So when the wave goes, it's going to bounce back. Reflect, if you will. Okay. So if I send a pulse and then another pulse, there's some point where those two pulses are going to interfere with each other. Okay, experience interference. If I do multiple, there's going to be multiple points of interference. Okay, if I send a continual wave, there's going to be a lot of different points of interference. But at a certain point, if I shake it just right, I get a standing wave. Okay, some points are always experiencing constructive interference. Other points are always experiencing destructive interference. What points are always experiencing destructive interference? Along the slinky. Places that aren't moving. Everybody got that? The nodes. Okay. Points that are always experiencing constructive interference are the bulges, your antinodes. You can see the white piece of tape in the middle there. That would be an antinode. Okay. Notice the amplitude compared to how much I'm shaking. Okay. I'm not shaking very much, but the amplitude is huge because of constructive interference. You okay with that? Okay. Thanks, sir. You're going to have a chance to do this with a couple people. So what we're going to do, instead of using slinkies, we're going to be using long springs. Okay? So you're going to stretch it out, but not so much that it stretches to the point of like, you know, you like take a slinky and stretch it too hard and it doesn't come back. Okay? You don't want to do these with these, but there does need to be some tension in there, not tons. Okay? One major rule, don't let go. Okay? Hang on. One person's going to be the wave giver, like I was. The other person's going to be in post, like Josh was. Okay? The wave giver shakes, the in post just holds. Okay? You're going to try to make the different harmonics. So, like the first harmonic is going to look like a jump rope. Okay, it has a single bulge. Then go for the second harmonic, 2 bulges. Third harmonic, 3 bulges. And then after the third harmonic, you can go crazy, see how many you can get. Okay? And then once you go through all those, you flip roles, the other person becomes the in post. Good. And the wave maker. So you're going to have the slinky on the floor. We're going to go out in the hallway, spread out, need some tension, like start down here all the way to the length of the hallway. Please, other people are trying to teach, trying to learn, try to communicate in ways that are not a lot of volume. That makes sense? Okay. You're probably going to have to go in groups of 3, 2 or 3. See what happens. Until we run out of strings. Okay. Go. Come grab a spring. Spread out. Down the length of the hallway.
Saw that, I was like, oh, right.
Grab one and go.
Where's Parker? Where's Parker?
Okay. This is going to be kind of like a slow motion with what Josh and I did at the beginning. So we've got the waves coming in. Here's the slinky. This is Josh here. When it hits, it's going to reflect. And the reflected wave is going to interfere with the incoming wave in such a way that certain points are always experiencing destructive interference, your nodes, and other points are always experiencing constructive interference, the antinodes. Good with that? Okay. When you did this in the hallway, did a standing wave develop at any and every frequency that you shook it at, or were there specific ones like you had to work at it before you made the standing wave? You had to work at it, right? Like there was like, oh, there it is, right? And then you like change it. Okay, so there's only specific frequencies that make a standing wave. Okay? So you started with the first harmonic, fundamental frequency, and then you went to your second harmonic. Did you have to shake? And then the third, what did you have to do to make those higher and higher harmonics? You had to shake faster. You had to shake more frequently. You okay with that? So the equation that guides that is this. So this is N is the number of harmonics. This is your fundamental frequency. First harmonic. So to get your second harmonic, this would be, the second harmonic would be 2 times the first. Get your third harmonic, you go 3 times the first. So on and so forth. Did you buy that pattern? Like, is that something you're like, okay, yeah. We didn't really measure it, but okay, sure. Okay. So, the equation for a standing wave on a string is this. Or like the harmonic, the frequency of that is equal to the number of harmonics times the speed over twice the length. This is the speed of a wave on a string. And this is the length of the string. Okay, there. Examples of this would be stringed instruments. So anything that plays a note because of the strings. So like a violin, a cello, a guitar, harp, piano. All these are examples of stringed instruments, and they are defined by this equation. Okay with that? All right, so how so real quick example problem. We got a bass guitar has a length of string of 1.6 meters. I want to know the speed of the wave on the string if I'm playing the fundamental frequency of 75 hertz. I'm using this equation. So I have 75 hertz. N, fundamental frequency. This means N is equal to 1. Some vocab. Speed of the wave, that's what I'm looking for, over twice the length, 1.6 meters. I just solve for the speed. Multiply, then bring it over here, find that to be 240 meters per second. Not too bad. Yeah. So like that's the level of difficulty for this part, for the math. Okay. All right, so up here is the equation. That's you. Tell your neighbor what you think. Correct answer is A. If I make this smaller, the denominator smaller, that's going to make this bigger. Increase the frequency and increase pitch. Okay, so to change the note on a guitar, the easiest way to do that, put your finger on the fretboard and press down. Okay, so what I'm doing is I'm always playing the fundamental frequency. So when I play this, it's going to look like the string is going to look like a jump rope. If I could see this in slow motion. You're right with that? So this is a node, this is a node, this is an antinode. Okay. When I press this down, this becomes the node, and this becomes the length. All right with that? And that's typically how you change the note on a guitar. Okay. So another way I can change the note is by tightening it. And so what that does, there's an equation. You have tension, and then this is mass per unit length. So as I tighten it, that's going to increase the tension. Which is going to do what? Tell your neighbor. All right, two-step. Tension increases. That does what to the speed? Increases. If the speed increases, then frequency increases. Okay. So as I go from I'm tightening the string. Good with that. So I'm actually changing the medium because I'm tightening the string. Okay. So this mass per unit length, I have different sizes of strings. Okay. The skinny ones here have a less mass per unit length versus the thicker ones have more mass per unit length. Have you ever looked inside of the back of like a baby grand piano, like opened the hood up? The high notes are just single string, like wires, but like the bass notes, the lower notes, they're like really thick. They take a wire and they wrap it, take another wire and wrap it another, like coil it around another wire, and then they do that again. Because if you had a wire that thick that was solid, it wouldn't vibrate. So they make it kind of like a springish type thing to increase the mass. Good with that? So as the mass increases, what happens to the speed? Decreases. If the speed decreases, then the frequency decreases. Good? So all stringed instruments are governed by this equation. Good with that? Okay. Today is talking about how instruments work. Okay. Opened in tubes. So if you have an opened end tube, then the equation is exactly the same as a standing wave on a string. The difference is this is the speed of sound in air. It's 343 meters per second. Everything else is the same. This is the length of the tube. Okay? So examples of this would be wood and wind instruments. Clarinet, saxophone, recorder. Is that fourth grade that you did that? Pipe organ, bagpipes. Okay. Woodwind instruments. Opened into. So, the difference though is this: anytime you have an instrument that you're blowing into, the speed is going to be the speed of sound in air. This is a fixed value. You good with that? Okay. All right. So one example. Of this is a flute. So the flute, a flute is an open-end tube. One side's open, the other side's open. Both ends are open. Okay. So when you play kind of like you don't blow into the open end, you blow across it. Kind of like blowing across a Coke bottle. Okay. Okay. And it causes a standing wave inside the pipe. You all right with that? Okay. Now, this gets a little dicey. So I'm starting with all the buttons closed. Should have made you answer the question first. Note. So, low pitch, high pitch.
Like there's no negative.
There is.
It is a frequency.
Okay, so the way we measure, like the way we measure okay, correct answer is B. As this gets shorter, this goes up. Okay. That's gorgeous. That was the best yet this year. All right, good with that? Now, here, what we see is an animation of a longitudinal standing wave with the dots represent air molecules. Okay, these are open-end tubes, so this is the length of the tube. This side's open, that side's open. At some point, these air molecules aren't moving anywhere, so this would be a node. These points are moving all over the place, so you got an antinode. Node, antinode. If you're looking at motion. If you're looking at pressure, this part's going from high pressure, low pressure, high pressure, low pressure, high pressure, low pressure. Here in the middle, it's just staying normal pressure. Okay, so depending on how you describe it, but does that make sense? You have it, how you have a standing wave. Okay, so that's what's going on inside a tube. Okay, so when I do this, I can also change a note by going. So what happened from a physics point of view? Yeah, but what did that change? What did that change in the equation? Talk to your neighbor.
It's the same.
Can I change the speed of sound in air? Cannot change the speed of sound in air. That is always 343. So what did I do? What did I change? The harmonics. I went from the first to the second harmonic. You okay with that? Okay. So here I have a tube that has both ends open. Okay. First harmonic. Second harmonic. Third harmonic. Fourth. Good? You guys bring that to a basketball game or something. Okay? All right. Standing wave in a closed-in tube. So this is a closed-in tubes are one that has one end closed, the other end open. It is the same equation as a open-end tube, except it's 4L in the denominator, not 2L.
Is that because that's a bounce back?
Great question. I know the answer. I'm just trying to figure out how.
Well, is it because like
Deep.
if it's the closed side, it has to bounce back, so it's double it?
Here's the. I'm going to try and make this answer as fast as possible. So, for a closed-in tube, this is what the standing wave looks like in terms of pressure. There has to be a node at the closed end. There has to be an antinode at the open end. What fraction of a wavelength is that? So a wavelength would actually be that. So it's a fourth of a wavelength. That's where that comes from. Okay. All right, so this still needs to be 343 meters per second. Okay, with that. And examples of this are brass instruments. Okay. Now, let me give you this disclaimer. These are simplified. The physics that goes into instruments is really complicated. People have got their PhDs on understanding how instruments work. The way the instruments have evolved is like they're like beat on a log, like, oh, that was cool. Like just beat on another. Oh, like oh. And over time, instruments have evolved just because of trial and error. Like, oh, that sounds cool. Like, who would do that? And no one ever. I mean, people might have asked, "Well, how does that work?" I don't know. It just sounds cool. Like, okay, let's keep doing it. And so we never really understood it until we, like, recently in the history of mankind, we are going back and trying to figure it out, and it's crazy complicated. So this is a simplistic model of how all brass instruments work. And there's been arguments like a double reed instrument, that's probably a closed-in tube, and a single reed is an open-end tube. And so I'm not really worried which category it falls into. On a test, I will tell you this is an open-end tube. And you're like, open-end tube, it goes with the other equation. No, I'll just do that. Okay, not trying to make it complicated. Okay, so brass instrument. So when this part here that you put your mouth on, this is closed in, this is your open. Okay, so the source of all sound is vibrations. And that comes from vibrating your lips. I'm doing it in a mouthpiece. Notice I can do that at any and all frequencies. But when I do it into the pipe, into the tube, I only get certain frequencies. Just like when you're shaking the spring, you didn't get a standing wave except at certain frequencies. Okay? And so when I'm doing this, I'm changing the harmonic because I can't change the speed. Correct? Okay. So if I increase the length, what's going to happen? As I increase the length, good. Okay. Trombone's easy to see on other brass instruments when you play, when you press valves, that actually opens other tubes up to change the length of the tube, the path that the air travels. Good with that? Okay. All right. So here, I have a boom whacker. Okay. Open in a tube. If I make that closed in, what is that going to do? Make it a closed in tube. What are we going to do? Have a conversation.
It's not the line.
Whirly pipes. Good. So, what do you say? Okay, goes down. We went from 2L to 4L. So the denominator increased, therefore the frequency goes down. Good? Okay. Last question. Tell your neighbor what you think.
The L is on the now make the pitch smaller, right?
Okay, which one has the longer tube? Hey, open in. The frequency, watch, the frequency stays the same. The N stays the same, still a fundamental frequency. The speed stays the same. So in order to make the denominator the same, this needs to be, this one needs to be, to make this long, like here I'm 4 times L, I need to make this bigger than this one. Okay, so here is, that's the short one. I put the end on the short one. Good? Okay. So you have a worksheet. I debated a question for you. I tried not to give you homework over the weekend. If I say it's due tomorrow, you won't have homework over the weekend. But I'm not going to check it till Monday.
So we don't need
So if you don't want homework over the weekend, pretend it's due tomorrow. And all you procrastinators, you have homework over the weekend.
Monday morning.